Welcome, everyone. Today, I am excited to introduce Shannon, our cutting-edge solution for autonomous penetration testing. In this session, we will take a deep dive into the core architecture, the advanced capabilities, and the strategic deployment of this specialized AI agent. Shannon represents a significant leap forward in cybersecurity, combining intelligent decision-making with automated testing protocols to identify and mitigate vulnerabilities more efficiently than ever before. Let's explore how this technology is transforming the landscape of proactive digital defense. Moving from traditional scanning to agency represents a fundamental shift in how we approach security testing. Shannon is an autonomous AI agent designed specifically for white box testing, operating on the core principle of proof by exploitation. To understand how Shannon functions, we can look at three key pillars. First, in terms of its type, Shannon is a true agent. It utilizes a self-driving autonomous workflow that requires no human intervention once the process has started. It makes independent decisions to navigate and test the environment. Second, the methodology is strictly white box. Shannon requires full access to the source code to thoroughly understand application logic and internal routes. This level of access allows the agent to perform a much deeper analysis than traditional black box tools. Finally, the output consists of verified exploits rather than theoretical alerts. This approach eliminates false positives by providing concrete evidence of vulnerabilities. Shannon generates comprehensive reports that include screenshots, database dumps, and reproduction proofs, ensuring that every finding is actionable and confirmed. To understand the evolution of vulnerability detection, we must look at the fundamental shift from pattern matching to reasoning. On the left, we see traditional scanners. These tools rely primarily on heuristics and regex patterns to identify potential issues. While broad in scope, this approach is inherently noisy, producing a high volume of false positives. Traditional scanners flag theoretical risks, but lack the capability to verify them, resulting in a chaotic mess of data that security teams must manually sift through. In contrast, the Shannon agent represents a new philosophy based on active reasoning. It operates with the logic of a junior human pen tester, moving beyond simple pattern recognition. Instead of just flagging a potential match, it formulates a hypothesis and then proactively tests that hypothesis via a browser. By verifying every finding through interaction, it effectively eliminates false positives. This transition moves us from a state of high-noise uncertainty to a clear, validated output where every reported issue is a confirmed reality. The agentic workflow follows a structured four-stage process designed to automate security assessments. It begins with reconnaissance, where the system ingests the code repository to map API endpoints and analyze authentication logic. Next, in the static analysis phase, large language models are utilized to identify dangerous code patterns. This leads into dynamic exploitation, where the system generates active payloads and employs a headless browser to attack the running application and verify vulnerabilities. Finally, the workflow concludes with reporting, which generates a comprehensive reproduction guide, complete with evidence to facilitate effective remediation. This slide details our primary capabilities and the specific attack surface we address. Our core focus centers on critical OWASP Top 10 vulnerabilities, specifically targeting SQL injection, cross-site scripting, and server-side request forgery. We also emphasize detecting authentication bypasses, including insecure direct object references, to ensure data integrity and security. For more advanced execution, the platform utilizes a white box approach, requiring visibility into the repository structure for deeper analysis. Additionally, we employ sophisticated browser automation to manage complex session tokens and login flows. This allows us to effectively test modern, JavaScript-heavy frontends, providing a more comprehensive evaluation than standard automated tools. The central challenge we face is the inherent trade-off between precision and the consumption of time and tokens. When we prioritize precision, as illustrated on the left, we achieve exceptional accuracy. This method focuses on verifying exploits to systematically eliminate false positives, providing a level of reliability that is critical for sensitive operations. However, this precision comes with notable drawbacks in terms of speed and cost. On the right, we see that performance is significantly slower, with individual runs requiring between 30 minutes and 2 hours. Additionally, the high token usage drives up operational expenses, ranging from $10 to $50 per run via API. This visualization underscores the need for strategic decision-making to balance the demand for accuracy against the practical constraints of time and budget. Moving into the operational assessment, we evaluate the practical advantages and limitations of integrating this solution. Starting with the benefits, the tool provides a strong proof of concept by delivering working payloads, which drastically reduces the time required for triage. It also operates with low noise, effectively filtering out theoretical or non-exploitable issues that often clutter automated reports. Most importantly, it is context-aware. It goes beyond simple detection to understand exactly why a vulnerability exists within the specific logic of the code. On the other hand, there are several drawbacks to consider. Operationally, it is an expensive option, carrying significantly higher costs than traditional free scanners. We must also account for tunnel vision, where the system may overlook complex business logic flaws that require a broader architectural understanding. Finally, there is a notable privacy risk, as source code must be transmitted to third-party large language models for analysis. Weighing these factors is essential for determining how this tool fits into our overall security posture. These critical safety protocols are mandatory for the use of Shannon. First, there are to be no production runs. Shannon performs mutative actions, including dropping tables, inserting garbage data, or corrupting state, and must only be operated in staging or test environments. Second, we must address data privacy and compliance. Using Shannon implies sending code-based snippets to external LLM providers, such as Anthropic and OpenAI. It is essential to verify compliance with your internal data handling policies before proceeding. To ensure a smooth deployment, there are 3 essential prerequisites we must address. First, in terms of infrastructure, Docker and Docker Desktop must be installed to manage our containerized environment. Second, for the logical engine, referred to here as the brain, you will need an Anthropic API key. We specifically recommend using Claude 3.5 Sonnet for its superior performance in coding and complex reasoning tasks. Finally, you must establish the target, which consists of your local source code and a live, running web application, such as the OWASP Juice Shop, to serve as the subject of the deployment process. Installation and configuration of Shannon follow a straightforward 2-step process. First, you need to retrieve the codebase. This is accomplished by cloning the repository from the provided GitHub URL and then navigating into the directory using the change directory command. Once the files are in place, the second step is to connect the system's intelligence, which we call the brain. You will need to create a .env file in the root directory of the project. Within this file, you must define 2 essential environment variables, your Anthropic API key and the LLM provider. This configuration ensures that the system is properly authenticated and ready to interface with the language model. Preparing the target environment is a critical step in facilitating a white box security assessment. Shannon operates under a white box requirement, meaning it must be able to read and analyze the victim's source code to function effectively. To set this up, you need to clone the target application's source code directly into the designated repos folder. As illustrated in the directory structure, the repos folder resides within the Shannon root directory. In this example, the Juice Shop repository has been successfully integrated alongside a folder for other potential target applications. This specific organizational structure ensures that Shannon has the necessary direct access to the codebase required for its analysis. Now we are ready to launch the attack using the command /Shannon start. When running this, you need to provide 2 essential parameters. The first is the URL, which we point to http://host.docker.internal:3000. This specific hostname is critical for Docker networking, as it allows the containerized tool to reach services running on your local host machine. The second parameter is the repo variable. While this example shows Juice Shop, you must replace it with the actual folder name located within your repos directory. Monitoring the agent effectively requires visibility into both its internal reasoning and its overall workflow. To observe the agent's thought process in real time, you can access the terminal logs by running the command /Shannon logs. This provides a detailed text-based stream of the agent's logic as it executes tasks. For a more visual overview, the temporal UI dashboard is available at http://localhost port 8233. This dashboard displays a graphical representation of the agent's state transitions and workflow progress, allowing you to track the status of individual steps and ensure the entire process is operating as expected. Once the execution is complete, you can find your results in the Reports directory. This directory houses Markdown files that provide documented proof of concepts, including the specific curl commands and payloads used. If you run into issues, there are 3 common areas to check. First, if you experience a connection refused error, ensure you are using host.docker.internal in your URL. Second, if you encounter rate limits, verify your API tier, as free tiers are restricted quickly. Finally, to free up system resources, remember to perform a cleanup by running the command sudo/Shannon stop. To conclude our assessment, we view this solution as a vital second pair of eyes for the modern development lifecycle. It is specifically designed for DevSecOps teams that operate with dedicated API budgets and established staging environments. By positioning itself as more intelligent than a standard linting tool, yet significantly more cost-effective than hiring an external human firm, it strikes an essential balance. Ultimately, it serves as a powerful instrument for proof by exploitation, providing a concrete and actionable layer within the contemporary security stack.